Hi again. So this is going to be the solution to the problem I asked you to try, the sphere rolling down the incline that's 5 feet high. And it starts from rest. The question is, what is its speed at the bottom? And it's like the problem with the bucket and the drum, but here both the thing that's translating and the thing that's rotating are the same thing, the sphere. So yeah, it's you can use conservation of energy because you are relating a change in position to a change in speed. That's the thing that um, suggests to you conservation of energy. It won't always work, and there may be other cases than that in which you'd use conservation of energy, but change in position related to a change in speed may well be conservation of energy. The question you ask then is whether conservative forces are the only ones that do net work, that are external to the system and do work on it. And here the sphere is acted on by gravity. The gravitational force is the only thing that does work on it. You'll have a static frictional force that will spin up the sphere, but static friction does no work because the point of contact between the incline and the sphere will be instantaneously at rest. It'll be static friction rather than kinetic friction because the sphere is going to roll without slipping. So because there's no displacement through which the static friction acts, it does no work. The normal force is not going to do any work because it always acts perpendicular to the direction of motion. And so the only external force doing net work on the sphere is the gravitational force. Gravity is conservative, and so you can use conservation of energy to relate the change in position to the change in speed. All right, so conservation of energy, you just write down E initial equals E final. Conservation of energy means energy doesn't change. Energy is kinetic plus potential. So the initial kinetic plus potential equals the final kinetic plus potential. The initial kinetic is 0 because it starts from rest, right? It's at rest when it starts, so the kinetic energy is 0. It's not moving. I'm going to say that y is equal to 0 at the top, and y is increasing upwards. So potential energy is 0, 2. For gravity near the surface of the Earth, it's mgy. I'm going to call y equals 0 here just to get rid of that term. It doesn't matter, but I'll call y equals 0 here, and y equals negative 5 meters here. Okay, and so you get 0 is equal to the kinetic initial. So kinetic initial is the kinetic of translation plus the kinetic of, I'm sorry, this is final, right? Yeah, E final. So the final kinetic is the kinetic final of translation plus the kinetic final of rotation, and then you have the potential final. And I'll come over here to get more room. So 0 is kinetic final of translation, which is 1/2 mv final squared, plus the kinetic, the final kinetic energy of rotation, which is 1/2 I omega final squared. And potential energy is mgy final, is the final potential energy. And we proceed just as we did for the last problem. So we replace the moment of inertia with the moment of inertia of a sphere, because that's our object this time. And it's a solid sphere. I guess that would be a good thing to tell you. I'll put that in the comments along with the other video when I post it. So yeah, I mean, if you see it, if I write sphere, I mean solid sphere. The moment of inertia of a solid sphere is 2/5. the mass of the sphere times the radius of the sphere squared. Omega final, because the thing rolls without slipping, is V final over R, and that's squared. And I'll just make a note over here. Omega final equals V final over R because you have no slipping. And so you get 0 is equal to 1/2 m V final squared plus 1/2 times 2/5. So I'll simplify that to 1/5 of the mass. R squareds cancel because that's an R squared also. So 1/5 mv final squared plus mgy final. And I want to solve for v final squared, so I'll bring the mgy final to the other side, and I get 1/2 m v final squared plus 1/5 m v final squared is equal to minus mgy final, because I subtracted mgy final from both sides. I can divide through by m, so I can get rid of all the masses, because m is in each term. Remember, in the last problem, we had two different masses. That's why we couldn't cancel the masses from the terms. All right. Notice, by the way, that this v final that I'm talking about is the final speed of the center of mass, because that's the point in the sphere that's translating. Since it's a uniform sphere, which we assume in a problem like this, the center of it is the center of mass, and that center of mass is moving in a straight line. That's the only point in the sphere that moves at the speed of the center of mass for the whole time. And so this v final is of the center of mass. Just a note on that. Okay, and right, so let me finish solving this. So we get 1/2 plus 1/5. I'll factor that out. V final squared is equal to minus the masses canceled gy final. And so I get v final squared. I divide by 1/2 plus 1/5 on both sides. Get minus gy final over 1/2 is 5/10. 1/5 is 2/10. So that's going to be 7/10. And so I get v final is square root of minus 10 gy final over 7. And right, so the question is, does the sphere reach the bottom with a higher speed or a lower speed than it would have if it had slid down the incline instead of rolling without slipping? And so ask yourselves, what would this 10/7 have been if it had slid? Which is yeah, ask yourself that, and I'll give the answer in a minute. So this is square root of minus 10. G is 9.8 meter per second squared. And y final is, remember, it's negative 5 meters because I chose the top to be positive. I chose the top to be y equals 0. So the bottom is negative 5 meters because y increases up, so it decreases down. Remember, y needs to be increasing upward for mgy to be the potential energy of gravity. So we get minus 5 meters there. And so that is over 7. And that comes out to be 8.37 meter per second. And so do you see the answer to the question? Is it going slower or faster, the center of mass, um, than it would be if it weren't rolling, if we're merely sliding. Well, it's going slower, right? Because some of the work done by gravity is going into spinning it up, into causing it to rotate. So not all of the work done by gravity is available to give it translational speed. So the translational speed is less than it would be if the sphere slid down the incline. And you can see just how much less. Remember, this amount here, this 10/7, would have been 2 if the thing had been sliding instead of rolling. And you can see that if you go back to the start, right? If the 1/2 I omega final squared weren't there, this 1/2 would show up as a factor of 2 here. Which you might remember that B final is root 2g minus 2g delta y. Okay, I mean, if something's just falling, falling with no rotation. Okay, so thank you very much for your time, and I hope this has been useful, and I hope you have a good rest of your day.